So in 8.1, we also want to look at what happens when our original population is not normally distributed. So for this example, we're looking at a six-sided die, and we know the probabilities of a fair six-sided die would be a 1/6 chance of landing on any one side. And so the probability distribution would look like this. It would look like a uniform distribution with each outcome having equally likely chance of occurring. Now, certainly not normal. What if we were to take this distribution and look at samples from a die roll? So let's say we looked at rolling a die 4 times and what the mean was of those 4 die rolls. That's what we're talking about here with a sampling distribution. Let's say we did that 200 times. Here's a model of saying 200 random rolls or 200 sample means from 4 random rolls. So obviously sometimes you're going to roll high. You might roll all 6s to where you have an average of a 6. Sometimes you might roll all 1s, 4 1s, so your sample average is a 1. Lots of times you're going to roll something in between, or some low, some high, and end up with samples toward the middle. So it makes sense that there's more of these than there are of the extremes. Right? Certainly less likely to roll 4 straight 6s or 4 straight 1s than 4 numbers that would average to something in the 3 to 4 range. That's what this is showing us. Well, let's take that same number of trials, but let's increase the number of rolls that we're using to find the mean. Let's increase it to 10 rolls. Well, now when you roll a die 10 times, it's that much less likely you're going to roll 10 1s or 10 6s. So we see those bars representing those averages drop significantly. Still, more likely when you roll a die 10 times, that the numbers you roll will average to somewhere there in the middle, between 3 and 4 roughly. You'll still have some of the extremes of low and high, but not that many in comparison. Let's increase that sample size further to saying we're going to roll the die 30 times and look at the sample mean you get from 30 die rolls. Again, very few expected rolls of 31s or 30. And notice, these aren't even representing 1s and 6 anymore. We've really zoomed in now to where this is an average of 3, this is an average of 4. So here we're looking at an average of maybe 2.5 here and 4.5 there. So we aren't even seeing the histogram bars because they're so low for those averages of 1s and 2s or 5s and 6s because of the chance of rolling a die 30 times and having an average that low or that high is so small. But even more important than that is you now see more clearly than perhaps either of these distributions a symmetric bell-shaped curve. And so this is just an example of what exists as a rule that we call the central limit theorem. And there is effectively this magic number for any distribution, whether it's uniformly distributed or has some very weird, indescribable distribution of the numbers in the data set. No matter what your data set, if you have a sample size of at least 30, if n is at least 30, we're going to say the central limit theorem, which we abbreviate CLT, will tell us that the sample means will have a distribution that will be approximately normal. So again, what we did is we took a distribution that had no bell shape to it whatsoever and took samples of size 30, and the means that came from those samples did have a bell-shaped curve, bell-shaped distribution. That's what the central limit theorem tells us, and it's very powerful. Because now what we can do, as far as examples, we can take a look at something like this. We're looking at the oil change time here. The mean time for an oil change at a shop that's going to say they can do it in 10 minutes is 11.1. Okay, that's their average. And the standard deviation of the time it takes them to change the oil is 3.2. Now notice in here, nowhere does it tell us that these times are normally distributed. Okay, it's not given to us. So we would not be able to just draw a bell-shaped curve if this was the only information we were given. Now what they're saying here is we're going to take a random sample of 35 oil changes and ask the question, what's the probability that the mean oil change time is less than 10 minutes? Okay, we're taking a sample, and most importantly, that sample, the sample size, 35, is at least 30. That's what we want to see. That's what tells us the central limit theorem applies here. And since it applies, we can say, just to put this in some symbology here, X bar, the sample means that distribution is going to be normal. So that means we can answer a question about the sample mean. So if that's the case, let's label the two other pieces of information we knew. We knew the population mean was 11.1 and the population standard deviation is 3.2. But what this means is we can draw this picture not for X. We do not know the oil times themselves are normally distributed, but we do know the means of them are. And so, with a mean of 11.1 known to be the center, if we're asking for less than 10, well, 10 is certainly left of 11.1, and less than 10 would mean we want to shade or look at that area right there. And then we want to convert that over to z-score world. So same picture, same idea, but we're looking for the z-score of that boundary there, which means we need our revised z-score formula, which was the x bar minus mu over sigma over root n. So plugging in our numbers, the x bar in question is 10. The mean that we know to be the center is the 11.1. And then sigma 3.2 over the size of our sample, 35. And we'll figure out what that z-score is. So 10 minus 11.1 in parentheses, divided by the 3.2 divided by the square root of 35. So there's what it should look like. There's my numerator. 3.2 divided by the square root of 35, my denominator. And that's giving me a z-score of negative 2.034 if I round. That is the label we can put down here as the boundary line. And then to get that area, we're looking at normal CDF. And since this goes off to the left, shaded left forever, we'll need our negative 10 or 100 up to the negative 2.034. Again, make sure to use your negative sign, not the minus sign when you're throwing those negatives into your calculator. And that's going to give me 0.02. It would be 0.9, but the 9 would round, so 0.1, so 0.210 for the probability, or the area under that curve. And so, as a sentence, we would say the probability a sample of 35 oil changes has a mean time less than 10 minutes is 0.0210. So it sounds like they may want to work on that because there's not a good chance that the average is below that 10-minute guarantee. So hopefully they're not offering refunds. All right. Another example. American family generates an average of 17.2 pounds of glass garbage each year with a standard deviation of 2.5. Again, notice no mention of normal. Find the probability that the mean of a sample of 55 families will be between 17 and 18 pounds. So we see the size of our sample is 55, which is at least 30, so we're good. That again tells us the CLT, which tells us that X bar. So the distribution of our sample means will be normal. That's good. Throwing the other information we have here, the population mean is known to be 17.2 and standard deviation of 2.5. So now we go to create what we know to be a normal distribution for X bar. Now if the mean, the center is 17.2, 17 to 18 would mean we've got 17 somewhere to its left, 18 somewhere to its right. And we're looking for the area between the two, from 17 to 18. So we want to convert that over to z-score world. Same picture, but we need some z-scores. So the z-score for 17 will be 17 minus 17.2 over the 2.5 over the square root of 55. coming out to negative 0.593. So that could be the label of that boundary. And then using the z-score for 18, thrown into that same z-score formula. Gets me 2.373. And so that means if we need the area of that shaded region, then we actually have both our boundaries. So we can put normal CDF negative 0.593 to 2.373. And come up with 0.7146 if we round. And not writing the sentence here, but this is the probability. Again, you just rephrase the sentence. The probability that the mean of a sample of 55 families will generate an average of 17 to 18 pounds is 7.416, 7.146. So this last page here, we have one setup, but two questions. Now you'll notice we have the average age of engineers is 37, standard deviation is 4, and assume the ages are normally distributed. We actually are going to need this in this case because notice the first question. The first question says, what's the probability that a randomly selected engineer is older than 38.2 years? So we're randomly selecting one person. That's important because that makes this actually a Chapter 7 question, right? A single data value from a population, that's a Chapter 7 question. We needed normally distributed to even answer this question whatsoever. So notice there's no mention of sample size because we're not dealing with a sample here. We're just straight dealing with a population whose mean is 37, standard deviation is 4, and we know it's normally distributed for the data world. And if 37 is the center, 38.2 will be somewhere off to its right. So 38.2, and we're looking for older than that, so we want to shade to its right. So that's the region we're looking for, which will then convert to z-score world. So same picture. We just need the z-score of 38.2. So remember our original z-score formula is just that. So 38.2 minus 37 over 4. Coming out to a 0.3. And then we're able to plug that in to a normal CDF of 0.3 off to the right. So 0.3 to 10. And that's giving me a 0.3821 if I round. So writing the sentence here, we will say the probability that an engineer, you can definitely throw in the word randomly selected as additional information, but right here we're talking about one person, one data value. The probability that an engineer is older than 38.2 years is 0.3821. Complete coincidence that those 38.2 and 0.382 are there. But that would be the answer to that question. Now going to B, same situation, but if we have an engineer firm employing 25 engineers, find the probability the average age of that group is 38.2. So we have a group that we want their average. They don't use the word sample in there, but that's what we have, a sample mean. Now notice 25 is less than 30, but that's okay because we have that the distribution is normal. We do not need the central limit theorem. We do not need a sample larger than 30 if we're coming from a normal distribution. So with that being said, we can assume immediately that X bar is normally distributed because our original data set was normally distributed. And pretty much the same picture because the mean is still 37 and we're asking about 38.2. So 38.2 is out here. We're looking to its right. So we want the z-score picture shaded to its right. And we can find that value by using our new z-score formula, the X bar minus mean, over sigma over root n. So that will be our X bar of 38.2 is the question. The mean is still 37. Sigma was 4, and the size of our sample is 25. And that's coming out to be 1.5. So that is our z-score labeled that boundary. And so we can go to a normal CDF of 1.5 to 100. .0668 to 4 places. So that's our probability. And so the difference in the sentence now will be the probability that, and we could say a firm, you could put a sample of 25 engineers has an average age of greater than 38.2 years is 0.0668. So now we're given that sample size and saying we're talking about the sample mean, the average in that sentence, to interpret our final answer there.